any delay on the problem set will just be prolonging the inevitable. So, oh, yeah, there we go. Okay, I think we are now recording. So, good afternoon again, everyone. Anna, Jonathan, and Oriel. Ngayon, ipapagpatuloy natin yung discussion about unit number 3. And as I mentioned before we started the recording, I'll finish half of the remainder today and the remainder on Tuesday, even though I think kaya ko itong paspasan at tapusin today. So medyo relax lang tayo ng konti. I think we have enough time to cover the rest of last one, 5. I don't know. So last time we talked about continuity, and we sort of generalized the notion of continuity that we learned in undergraduate. Hindi pala undergraduate kasi undergraduate pa tayo, no? In elementary calculus na ang mga continuous functions ay yung mga functions at yung mga functions lamang na kaya nating i-drawing yung graphs without lifting our pen. But we learned last time that since now we are catering to a larger class of functions, specifically those functions whose domain are not necessarily expressible in terms of open intervals, na kailangan nating mag-admit ng isang wider definition for continuity in the same manner as we did for limits, right? So kasi ngayon nakadepende na ngayon sa domain yung pagtingin natin about continuity, because we had the result last time that tells us that any function is continuous at any point of or at any of its isolated points. So pag meron kang isolated point dun sa domain, automatic by default, di naman by default, but by definition, the function becomes continuous on that number or on that isolated point. And basically, ito ay medyo magdi-debunk dun sa ating characterization ng mga continuous functions to be those and those functions that lifting our pen. Kasi halimbawa si x sub 0 nagkataon ay isolated point. So before we go to x sub 0, medyo merong gap between x sub 0 and its closest co-member of the domain coming from the left and another element of the domain coming from the right. So in the space between x sub 1 and x sub 2, we cannot find any other member of the domain aside from x sub 0. And basically, that the absence of domain elements in some neighborhood of x sub 0 renders the possibility or renders sketching the graph of f without lifting our pen virtually impossible. All right? Kasi, okay, kaya kong i-drawing possibly kung nicely behaved talaga yung function, kaya kong i-drawing yung graph niya mula sa kaliwa ni x1 without lifting my pen. The same thing happens from x2 all throughout the right. Pero dahil wala namang domain elements dito sa interval na to, sa interval x1 to x2 aside from x sub 0, so it is unfair to require drawing the graph without lifting through x sub 0 kasi wala naman talagang dadaanan na function values doon sa immediate neighborhood ni x sub 0. In our math 36 definition, this might not qualify as a continuous function, right? Because the limit from the left of x sub 0 and the limit from the right of x sub 0 both doesn't exist. But under the framework that we developed from here in Math 155, x sub 0 is an isolated point, all right? So therefore, it is almost vacuously continuous at x sub 0, almost virtually default na siya ay nagiging continuous. So this can be seen as a continuous function, all right, over its domain. But in the main elements intervals, okay? Kasi x sub 0 ay isang isolated point. Pero kapag walang isolated point yung ating domain, then the idea of continuity based on the graph that we learned in Math 36 still applied. Lalo na dun sa mga intervals. Kasi sa mga intervals, where na-require natin na dapat madrawing yung lifting our pen. Kasi may mga domain elements sa pagitan na malapit kay x sub 0. So there's really some function values that must be passed in order to sketch the graph over the entire domain. Pero kung isolated point yan, huwag mong hanapan ng function value na dadaanan yung graph dito sa kaliwa at sa kanan. Kasi by default or by definition, yung function ay walang function values sa mga points na yon. Okay? And then we also tied up the concept of continuity with the concept of sequential limits. And we said na ang isang function ay nagiging continuous sa isang number kapag kahit anong sequence ng domain elements na nagko-converge papunta kay x sub 0 ay dapat nag-give birth sa isang sequence, sa sequence of function values that will converge to f of x sub 0, right? So yun yung characterization natin about continuity. All right. So dahil dumating na si Charles, pwede na nating simulan yung discussion about continuity on a compact set. Right? So ang idea ngayon ay, okay, maganda kasi yung behavior ng mga continuous functions. And usually, oh, that's fine, Charles. I'm just trying to crack up some jokes. So yeah, it's fine. Nasa na ako. Yeah. Meron kasing magandang, meron hello, guys. Can you tell me if I'm back? All right, thank you. Zero, no internet access kasi sabi ng laptop ko. So, yeah. All right, so yan, wala pa rin signal. Ayun, nakita ko na yung signal bar sa laptop. Okay, that's good. Now, meron kasing something na maganda about continuous functions. There's some good property between continuous functions that led the early versions of calculus to only admit continuous functions. And it is not just after we formalized or axiomatized real analysis, saka na discover ng mga mathematician na hold on, hindi pala fair na gawin nating exclusive ang study of calculus to continuous functions because there are some functions that are discontinuous and yet they do have significant implications in other mathematical sciences and even in applications in the physical, natural, and social sciences. Kaya nung mga 1800s, okay, kailangan nating punan yung mga butas ng 1600s na calculus, no, or 1600 version ng calculus. Now, one thing is that, okay, yung meron kasing principle sa real analysis na sinasabi, ang tawag ay Littlewood's principle, na yung mga nicely behaved functions, sila ay almost continuous functions. Because really, continuous functions, maybe you can think of it as the gold standard with respect to the behavior of functions. Sila yung mga sila yung best in GMRC, best in behavior among the class of functions kasi madaling i-predict yung behavior nila. Yung pagiging increasing, decreasing, by how much, yung derivatives nag-exist, yung integrals nag-exist. Marami siyang gustong property, or marami siyang properties na nakukuha that is nice from the calculus point of view. Now, this brings forth some interesting questions about continuous functions. Does it preserve, is it nice enough to preserve some properties of the domain? So titingnan natin ngayon, kapag ka ba yung mga inputs ko dun sa function ay galing sa isang open set, yung makukuha ko ba mga function values will constitute an open set as well? Another question, paano kapag ka kumuha ako ng isang closed set na subset ng domain? Pag isinalpa ko sila dun sa loob ng function, kinuha ko yung mga resulting function values, yung set ba na yon ay closed pa rin? Kung compact yung mga domain elements, compact pa rin ba yung function values? And that's what we will try to see here in this section 3.4. Okay? But before going there, napanood niyo ba guys yung recording ko dun sa composition of functions? I hope you did, because there I defined what is the image of a subset of a domain, of the domain. But sige, tingnan natin siya ulit. Nandito naman siya sa 3.4, right? So sabi rito ay, kapag ka meron kang isang function f na ang domain niya ay si set E, alright? Tapos kumuha ka ng isang subset A ni E, i-define natin yung image ng subset A na yon under f by this set. This is basically just the set of all function values of domain elements coming from capital A. So ang idea, kukuha ka ng isang subset ng domain, i-plug in mo yung mga elements ng subset na yon papunta kay F, kolektahin mo yung mga function values na yon, ang tawag natin sa set na yon ay yung image ni A under F. And we shall denote it by F bracket A. So F bracket A is actually a set. This is the set of all function values of x's coming from the set A. And then we say that F is bounded kung bounded yung F bracket E. So kung yung range, because basically si E yung entire domain. Pag pinlogin mo yung mga function, yung mga elements ng buong domain into the function F, what you'll get is the range of your F. So F bracket E is essentially your common notion of the range of F, right? So bounded ang isang function kapag ka bounded yung domain niya. That means we can find a lower bound and an upper bound for the elements of the range. And then we can extend this further to an arbitrary subset of the domain. Sasabihin natin si F ay bounded sa isang subset ni domain. Tawagin natin A yung subset na yun, even only if F bracket A is bounded. Okay, so if the function values of elements of A are bounded below and bounded above, then we say that F is bounded on the set A, right? And in that terminology, I can phrase yung mga questions na pinost ko sa inyo kanina. Yung ano ba yung mga properties na napreserve ng isang continuous function. So if I get an open subset of the domain, halimbawa si A, assume ko siya ay open. The question is F bracket A also open? Okay? That means, can continuous functions preserve the openness ng pagiging ng isang set? Pag meron akong open set, I let the function F operate on that function F, will I get back an open set? Also, kung meron akong closed set, ilagay ko yung mga elements ng closed set na yon sa loob ng function F, I harvest the results. Is F bracket A also closed? And then the same question will be posed kung compact naman yung subset ng domain. The first two questions can easily be addressed, and they are addressed in the negative. Usually, madaling mag-prove ng negative answer sa math, ng true or false. Kasi lalo na kapag yung statement mo claims something is true for all elements of a universal set. So it suffices to simply show one case for which the statement is false para mabelay yung statement. Alright? Mas mahirap yon pag magpo-prove ka na true kasi pag sinabi mong true, dapat meron kang isang proof na mag-hold sa lahat ng possible elements ng universal set. Okay. For instance, the answer about preservation of openness ay hindi totoo. Ibig sabihin, merong mga open sets na pag ipinasok ko sa isang continuous function, yung image ng open set ay hindi necessarily open. All right? And that is what this paragraph is telling us. Okay. Ang example na ginamit, of course, you can think of other counterexamples, but we have a simple counterexample here. We consider the quadratic function x squared from one of the, I think, statements in the previous section. We have said na kapag ang mga polynomials at ang mga rationals, sila ay mga continuous functions sa kanilang domain. Now, x squared is a polynomial function. It's defined everywhere, so it is continuous everywhere. So indeed, f is a continuous function. Now, let's consider the open. Now, na ang isang open interval ay automatically isang open set. Hindi na kailangang i-prove yun. Kailangan niyo na lang i-memorize yan. So kapag ka open set, sabihin nyo, sir, by default, alam na natin yan. Matagal na yan na isang open interval. Sorry. Pag meron kang open interval, alam na natin dati pa na yan na isang open set. So A is an open set. But if we plug in members of the open interval -1 to 1 into the quadratic function x squared, what we get is the image f bracket A equal to the half closed, half open interval 0 to 1. Kasi pag nag-plug in ka ng kahit anong miyembro ng set na to, x's that are strictly greater than -1 but less than 1, what we get back as our answer is an f of x that is greater than or equal to f of 0, greater than or equal to 0, but strictly less than 1. And we know that half open and half closed intervals are neither closed nor open. So nakita natin ngayon, meron kang isang function na continuous sa isang open set. Pero yung image, f bracket a nung open set na yon ay hindi open. So that means continuity does not always preserve pagiging open ng isang set. All right? Does that make sense? Isipin nyo ngayon, sir, ano naman ngayon kung hindi yan open? Well, there would be some topological implications for that, okay? Ang totoo kasi, kung di ako nagkakamali, sa topology ang sabi ron ay the inverse image of an open set is also open. So, kung meron kang open na f bracket A, sure ka na yung A ay open. Pero yung pakabila ay hindi totoo. Alright? So, kasi may mga open sets na may mga continuous functions na continuous sa isang open set pero yung image ng isang open set ay hindi open. Pero yung pakabila ay totoo. Yung inverse image or inverse continuous image ng isang function ay na open ay open din. But that's more of a topology thing. So if you haven't taken topology, never mind. It's just the nerd in me who cannot pass the chance to mention that. Okay. Now, tingnan naman natin yung pagiging closed. Kaya bang ma-preserve yung pagiging closed? We have a single paragraph talking about that, so most probably the answer is in the negative. Ibig sabihin, meron mga continuous functions sa isang closed set kung saan ang image ng closed set na yon ay hindi closed. All right? One particular example is the function 1 over 1 plus x squared. The constant function 1 is continuous. The function 1 plus x squared is continuous, being a polynomial. And from the algebraic continuity theorem that we learned last time, the ratio of two continuous functions is continuous, provided that the denominator is not equal to 0. So those premises considered, we can say that G is indeed continuous on its domain, which happens to be the set of all real numbers. So kung continuous siya sa lahat ng mga real numbers, so it will be continuous on the closed interval consisting of all the non-negative real numbers. So remember, this guy is this is a closed set. All right? So yung set ng lahat ng mga non-negative real numbers ay closed. However, when we plug in all the members of A into G, what we get back as the image is this half open, half closed interval. Right? So may typo rito, dapat ito ay G. Okay? Kasi pag nag-plug in ka ng 0, makukuha mo ay 1 over 1, which is 1. That's why 1 is included in there. All right? Never tayo makakuha ng 0 kasi bakit? Never tayo makakuha ng 0 kasi yung numerator never naman magzi-0. So kaya ito ay open dyan. And then we cannot get any number outside of this set because, for instance, we cannot get negative numbers because 1 plus x squared is positive. 1 divided by a positive number will always be non-negative, or actually it will always be positive. All right? So bawal yung mga negative. Tapos wala nang lalampas pa kay 1. Bakit wala nang lalampas kay 1? Kasi kapag ka nag-plug in ka ng any number that is greater than 0, okay, the denominator will become greater than 1. And you have 1 divided by something that is greater than 1, that will always be less than 1. So indeed, G bracket A is this half open and half closed interval, which we have mentioned earlier to be neither open nor closed. So ibig sabihin, we have a continuous function on a closed set that cannot preserve yung pagiging closed nung set na kinonsider natin. So yun, hindi nga na-preserve ng isang continuous function ang pagiging closed. Okay? And that's a little bit mind-boggling kasi sabi natin kapag meron kang isang closed set, ibig sabihin closed and bounded yan. Kung siya ay closed, kung meron kang closed set, hindi pala closed and bounded. Kung meron kang closed set, ibig sabihin lahat ng mga limit points ni A ay laman niya, And it's a little mind-boggling because we know na, kung may limit point ka, laman mo lahat ng limit point mo, it seems that there will be nothing wrong. It seems that everything under a continuous map will behave nicely. All right? So yun yung parang thinking, all right? Kasi limit point ka nga, so continuous, wala kang isolated point. So dapat nag-work seamlessly yung mga continuous functions. But apparently, it is not. There are some functions on which hindi nag-hold yung ating yung mga magandang properties ng pagiging closed, and even continuity added on top of that. Okay? Now, what could be the problem? One problem is the unboundedness ng function, nung set A. All right? Kasi parang nagkakaroon tayo ng problema when A becomes very, very large. So, itong value na to, never siya nag-approach ng, tama ba? Pag malaki na matter, mag-approach siya ng 0 pero hindi siya nagiging equal kay 0. Okay? So, parang yun yung nangyayari rito. So, ibig sabihin, yung mga function values, mag-approach siya in the long run kay 0 habang palaki ng palaki yung mga x's, pero the problem is 0 is not part of the range kasi hindi to ever magiging equal kay 0. So posible itong mag-approach ng 0 as x becomes becomes indefinitely large, pero hindi siya nagiging equal kay 0 kasi si 0 wala dun sa range. All right? So yun pala, doon tayo mukhang nagka-problema. So the question is, how can we remedy this? What could be imposed on top of pagiging closed in order for continuity to preserve that property of the set? And apparently the answer is boundedness. Kung closed na pala yung function, assume mo lang na siya ay bounded. Kung bounded din siya at saka closed at the same time, then those two properties can be preserved by a continuous function. Meaning if you get a closed and bounded set, its image under a continuous function will always be closed and bounded. Pero does being closed and bounded remind you of something? Something that starts with the letter C? Or kinalimutan nyo na talaga? If I'm not mistaken, it's also a reading assignment. So, have you done your homework, guys? Tandaan niyo pa, ano yung meron kung closed and bounded ng isang function? Thank you, Anna. That's perfect. It's compact. All right? Yun yung isa nating characterization sa pagiging compact. We had a theorem from Unit 2 that tells us that the set is compact if and only if it is closed and bounded. All right? So pag tinapunan ko to ng pagiging bounded, magiging compact na siya, and I guarantee you that compactness is preserved under continuous maps. And that's what we will prove in a few minutes. Now, before going there, i-recall muna natin yung definition talaga ng pagiging compact. Yung pagiging closed and bounded, though some books treat that as the definition of compactness, all right? Sa atin, hindi yun ang in-adopt natin na definition ng pagiging compact. Sabi natin, a set A is compact if and only if for all sequences, if and only if all sequences in your set will converge, not will converge, hindi necessarily nagko-converge lahat ng set, lahat ng sequences, pero kapag ka meron kang sequence sa loob ng isang compact set, we are guaranteed to have a subsequence that will converge to an element of the compact set. Okay? So, nagiging compact ang isang set kapag kahit na anong sequence na nasa loob ng set na yon will have a convergent subsequence that converges in the set, in the compact set itself. So dapat hindi lang nagko-converge yung subsequence, pero yung limit dapat ng subsequence ay nasa loob ng set E. So yun yung kailangan para maging compact by definition. Pero na-prove natin before na kapag ng isang set ay compact if and only if siya ay closed and bounded. So we will shift between those two characterizations of compact sets, all right? Depende kung ano yung mas madaling gamitin sa ating proof. But unfortunately, dun sa theorem 3.6, mas gagamitin ko yung definition kaysa dun sa pagiging closed and bounded. All right? So, yeah. And this is what I'm telling you kanina, na preserve yung pagiging compact ng isang set. Let's say you have a function f with domain E, and f is continuous on the entirety of the set E. Then if you get a compact set or a compact subset of the set of the domain, then the image of that subset K will also be compact. Kung compact yung input sa isang continuous function, yung output ay compact pa rin. Okay, and then let's see how this is proven. Now, unfortunately, when I was reading the uh, the lecture notes kaninang umaga, umaga pa ba yun? Mga 10 o'clock, late na ako nagising. So, binabasa ko siya, and then I discovered some little typos and some missing details, and then I checked bakit hindi ko to na-correct dun sa huling version from last semester. Yung pala kasi sinulat ko yung proofs independently. Tinakluban ko to, tapos nagsulat ako ng sarili kong proof. Kaya siguro nakalimutan kong i-edit. So to avoid that from happening again, what we'll do is for the remainder of the sections here, we'll just go over the proof. I-note natin yung mga kulang para matandaan ko siya na i-edit. So just make sure that before you do the problem set, you download first the latest version of the lecture notes to reflect yung mga changes o mga edits na ginawa natin in class. Probably I'll do that over the weekend. So I'll give you the go signal on Monday probably or Tuesday to download the latest version of Units 2 and Unit 3 para prepared kayo para sa problem set natin on next week. All right? And then, yun pala, speaking of, hindi ko pa rin nasisimulan checkan yung homework number 4. I know it's, kailan nyo nga ba siya pinasa? Within the week pa naman, no? So, hindi pa pala naman super late. Pero, para sa akin, parang late na siya pagka nakaabot siya ng 2 or 3 days na hindi ko na-checkan. Nagwo-worry na ako kasi parang hindi ko na nagawa yung role ko as a teacher sa inyo. Ano? So, pero I'll try to do it probably Friday or over the weekend, so you'll get it back before the 1 week period lapse. Because tomorrow I'll give you another homework, all right? Another short one, okay? Tapos ang deadline ulit ay Tuesday next week. Para maabot ko yung target ko na 8 homeworks for you. So yeah, I'll grade it over the weekend, but make sure to check Canvas tomorrow because I'll be posting homework number 5. Okay? And that will be due Tuesday next week. Tapos yung problem set, ibibigay ko siya probably Thursday next week. So wala tayong homework next week. Pero merong akong homework na ibibigay bukas na ang deadline ay sa Tuesday. Okay? So yun, tapos na yung commercial. Punta na tayo sa proof ng Theorem 3.6, the preservation theorem. Okay, so i-assume natin, meron akong continuous function f, tapos kukuha ko ng isang subset na compact ni E. Tawagin ko yung compact subset na yun na si K. What we want to show that f bracket K is compact. And we will do this by showing that f bracket K satisfies the requirement ng definition ng pagiging compact. That is, pag kumuha ko ng kahit na anong sequence na nasa loob ni f bracket K, gusto kong ipakita na lagi akong makukuha ng isang subsequence ni Zn na nagko-converge kay C sub 0 na miyembro naman ni f bracket K. So that's our goal here. Find that subsequence na nagko-converge sa isang element ng f bracket K because essentially what we want to show here na compact ay si f bracket K. All right? So let's see how this is done. Okay? Una, gagamitin ko yung definition ng pagiging element ni f bracket K. So meron akong isang arbitrary or isang random na sequence na nasa loob ni f bracket K. All right? So this proof will work for any such sequence that you can find. All right? So dahil bawat isang z sub n na element ng sequence ay nanggagaling kay f bracket K, ibig sabihin, merong element ng x sub, may element si K, tawagin natin siyang x sub n, na f of xn ay equal kay z sub n. Kasi remember, para maging miyembro ka ng f bracket K, dapat ikaw yung image ng isang element ni capital K under the function f. Dapat function value ka ng isang element ni K. So that means makakakita tayo ng isang xn or at least isang xn na nasa loob ng compact set K ng f of x n ay equal kay c sub n. Alright? Tapos, ayun ang gagawin ko. Sa bawat zn, pipili ako ng isang element ng tatawagin kong xn such that f of xn ay equal kay zn. So makakabuo ako ngayon ng isang panibagong sequence. Sequence ng mga xn na ang function values nila ay na kay f bracket k and in particular, they are equal to z sub n. Okay? Ang kagandahan dito ay yung sequence ng mga x sub n ay nasa loob ng compact set K. So, ibig sabihin, dahil siya ay, yung sequence ay subset ni K, si K ay compact, so may makikita kong subsequence, alright, ni Xn na nagko-converge sa isang element X sub 0 ni compact set K. Right? So dito, in-apply ko naman yung definition ng compactness kay K at dun sa sequence Xn. Alright? So, meron akong subsequence na x sub nk na nagko-converge kay x sub 0 na isang element ni capital K. Ngayon, di ba, gusto kong ipakita na si f bracket k ay compact, alright? Or hanapan ko ng convergent subsequence si Zn. Okay? Paano ko yung gagawin? Gagamitin ko yung isa pang bagay na crucial assumption na hindi pa natin nagagamit, which is the continuity of the function f on the set E and consequently on the set K. Alright? So dahil si f ay continuous kay E, ibig sabihin by the sequential characterization of the limit, pag kinuha ko yung sequence of function values of the x sub n case, so kukunin ko yung function value ni x sub n1, function value ni x sub n2, and so on, makakakuha ko ng isang bagong sequence. Dahil si f ay continuous, ibig sabihin magko-converge yung sequence na yon ng mga function values dun sa function value nung limit ng original sequence. So therefore, the sequence of function values ay magko-converge kay f of x sub 0. And so we have shown na, hindi pa pala, excited much? So, ano ngayon? So nagko-converge siya dyan. Alam natin na ang f of x sub nk ay equal kay c sub nk. Alright? Kasi nga sabi natin ang c sub n ay equal kay f of x n for all n. So pag naglagay ako dyan ng subscript, totoo pa rin yan. Ang z sub nk ay equal kay f of x sub nk kasi subsequence nga ni Zn yung c sub nk. So it is still true that z sub nk ay equal kay f of x sub nk. Pero yung x sub nk lahat ay nanggagaling kay k. So therefore, this is indeed a subsequence of f of xn. All right? And essentially, it will be a subsequence nung c sub n. So ngayon, halos kalahati na yung tapos natin. Napakita na natin na meron tayong isang convergent subsequence. Ano yung convergent subsequence na yun? Etong subsequence na to. Subsequence z sub nk equal to f of x sub nk. Convergent siya, pero nagko-converge siya kanino kay f of x sub 0. Now, it only remains to argue that f of x sub 0 is in f bracket k. Kasi kailangan para maging compact, yung limit ng subsequence dapat nandun sa loob ng set. And that is easy to argue because alam natin compact nga yung k, so yung limit na x sub 0 ng sequence na f sub nk ay na kay k din. Dahil na kay k si x sub 0, yung function value niya ay naninirahan sa loob ni f bracket k. So therefore, in summary, we have shown the existence of a subsequence c sub nk that converges to f of x sub 0, which is an element of f bracket k. And so therefore, we conclude by definition that f bracket k is compact. All right? Okay, so that's great. I'm seeing some reactions. So mukhang masaya kayo sa proof na yan. Ano? So sana ganyan ba yung mga nasa problem set? Pero if you think about it, kung babasahin mo lang, kung titingnan mo lang siya ng ganyan, nakita mo sa textbook, ay, X na yan. Ayoko na yung basahin. Kasi parang ang hirap niyang intindihin. Pero once you go into the detail, take it sentence by sentence, you will realize na oh nga no, simple lang pala yung proof. Mukha lang matalino yung nagsulat, pero anyone with rudimentary knowledge about compact sets and continuity can write a similar proof. All right. So that's why I usually think rewriting notes is a good practice, or even just rewriting proofs, because when you have textbooks, all right, and even materials in the internet, um, ang tendency ay may proof silang ipapakita pero hindi siya super detalyado. There would be little details that will be missed out, and it is a nice practice for you to fill in the gaps. Try to write or to rewrite the theorems or the proofs of the theorems in your own words, in your own formulation, kung paano mo siya gustong i-argue. So para ka ditong isang lawyer na nasa iyo yung mga facts of the case. Tapos gusto mong i-prove in front of a judge or a jury na totoo yung sinasabi ko, totoo yung claim ko, and these are the reasons. Reason number 1, reason number 2, reason number 3, and you collect evidence along the way to support all your claims. Mas mataas nga lang yung burden of proof dito sa math. Sa usual courtroom, it's either preponderance of the evidence lang or um, beyond reasonable doubt yung burden of proof. Pero sa math, absolute yung ating demand para sa proof. Dapat walang doubt at all. All right? So mas mahirap yung ginagawa natin dito. So that's it. That's the preservation of compact sets. You might ask, okay, sir, granted na napreserve ng isang continuous function ang pagiging compact, ano naman ang epekto nan sa atin? Is it just a nice result or does it have practical implications? Actually, it do have practical applications, and one of them is the very useful result na nakakilala nyo na simula sa math 36, and probably you encountered this again in your optimization theory classes, yung extreme value theorem. Medyo ano nga lang to, mas generic yung statement natin dito. Kasi kung matatandaan nyo sa Math 36, ang extreme value theorem lang natin, pag meron kang isang continuous function sa isang closed interval, alright, yung maximum at saka minimum ng function na yon ay isang function value within that interval. Alright? So ibig sabihin, we can say that a continuous function on a closed interval attains its maximum and minimum value inside the interval itself. Okay? Ngayon, medyo papalakihin natin ito ng konti. Hindi natin i-require na sa closed interval, but as long as you have a compact set, then your continuous function will attain a maximum and a minimum value on that compact set. Yun nga lang, nagkataon sa Math 36, wala pa tayong konsepto ng compactness, ano? Pero ang idea natin ay, ang nice example ng compact sets ay mga closed intervals because they are closed and bounded. So pero yung EVT pala, nag-work pa rin siya sa kahit na anong compact set. Alright? Now, medyo dadayain natin yung proof. Alright? Most of the work for the proof actually relies on lemma 3.1. Okay? Kaya nilagay ko na lang yung lemma 3.1 para maging exercise nyo na lang yung proof na yan. Tapos yung gist ng proof ng EVT will heavily rely on lemma 3.1. Ano ba yung sabi ng lemma 3.1? Kung meron kang isang compact set, then yung supremum at saka infimum ng compact set na yon ay nag-exist. At hindi lamang yon, sila ay mga elements ni set K. So you can think of, if you have a compact set, then there would be a maximum and minimum in the compact set. Kasi nga sabi natin kapag yung supremum at infimum ay nag-exist at equal sila at sila ay miyembro ng set, so ibig sabihin sila rin yung maximum at minimum. Alright? Which is basically kamukhang-kamukha ng extreme value theorem. Yun nga lang, lemma 3.1 can be construed as something talking about elements of the domain. Meanwhile, the EVT guarantees that for the function values. Okay? Now, try to construct a proof for lemma 3.1, pero ito yung idea, parang ito yung sketch, ano? So, para simulan niyo siyang pag-isipan, inisip ko ilagay ito as part of the problem set, but I'm not decided yet. Pag-isipan ko pa. Pero one approach is this. Assumption, K is compact. So kung si K ay compact, ibig sabihin siya ay closed and bounded. Meron tayong theorem na yon, compact if and only if closed and bounded. Dahil siya ay bounded, ibig sabihin meron siyang lower bound at saka meron siyang upper bound. So by the LUB property and its corollary, kung meron kang upper bound at lower bound, meron ka rin dapat greatest lower bound at least upper bound, which are essentially the infimum and the supremum. Okay? So we know that the supremum and the infimum exist. All right? Kailangan na lang nating ipakita na yon ay naroon sa loob ng set K. Yun yung medyo mas mahirap na claim na nandun sa lemma. But how can you argue it? Well, gagamitin natin yung isa pang property na hindi natin nagagamit. Nagamit na natin yung pagiging bounded ni K, gamitin natin yung pagiging closed niya. Alright? So isang paraan para sabihin niya, kukuha ako ng isang monotonically increasing sequence papunta kay sa loob ni K. Alright? So kukuha ko ng isang ng isang monotonically increasing sequence na kay K. Tapos dahil si K ay bounded by the monotonic convergence theorem, yung sequence na pinili ko ay magko-converge. Alright? Magko-converge siya, and the proof of the MCT taught us na yung limit ng monotonically increasing sequence na yon ay equal sa supremum nung set na yon. Alright? So, nung set na yon. Or nung sequence na yon. So, okay, so magko-converge siya sa supremum. So the supremum of that sequence will be the limit of the sequence. Pero closed nga si K. So ibig sabihin laman ni K lahat ng kanyang mga limit points. So kung yung sequence X sa bend K ay nagko-converge sa supremum. All right? So si supremum by our characterization of limit points ay isang limit point ng set K. At dahil limit point siya ng set K, dapat nasa loob siya ni set K kasi si set K ay closed. So the infimum of any sequence inside K is inside K as well. So you just need to stretch out that argument para masabi na okay, yung supremum nung buong set K ay kay set K din, katulad din ng infimum niya na nandun din sa sarili niya. Okay? So try to write a proof for that using those arguments. So iwanan ko na yung heavy lifting sa inyo, ipoprove ko na lang yung extreme value theorem. Anong sabi na, paano natin ipoprove yung extreme value theorem? Well, what are our assumptions again? Our assumptions is that F is continuous on a compact set K. All right? So, dahil si F ay continuous at si K ay compact, so therefore by the preservation theorem, si F bracket K ay compact. Right? Tapos, by lemma 3.1, dahil si F bracket K ay compact, nag-exist yung infimum ng F bracket K at saka yung kanyang supremum. Alright? Kasi papalitan ko lang dito yung yung K by F bracket K. Kasi ang alam natin na compact ay si F bracket K. So compact si F bracket K, so ibig sabihin yung supremum niya at saka infimum niya ay nag-exist. Tawagin ko yung infimum na C sub little m, tapos yung supremum C sub little m. Okay? Tapos dahil, tapos sabi pa nung lemma 3.1, hindi lang pala sila nag-exist. Pero yung dalawa na yan, pinangalan na nating Z sub little m at saka C sub capital M, sila ay nasa loob ni F bracket K. Kasi nga, lemma 3.1. Okay? Dahil si C sub little m at saka si C sub capital M ay parehas element ni F bracket K. Ibig sabihin, may mahanap tayong elements ni capital K na ang function value ay si Z sub M at saka si C sub capital M. Alright? Kasi nga elements sila nitong F bracket K, so this must be true. Alright? We can find an X sub little m and an X sub capital M whose function values are equal to C sub little m and C sub capital M respectively. Okay? Pero alam na natin na si C sub M at saka si C sub capital M ay ang infimum, greatest lower bound, and the supremum, least upper bound, respectively, of the set F bracket K. So therefore, sa kahit anong function value ng kahit na anong member ni capital K, lower bound nila si C sub M, upper bound nila si C sub capital M. Pero ano ba si C sub little m? Si C sub little m ay f of xm, tapos si C sub capital M ay f of x sub m. Ibig sabihin, lahat ng function values ng mga elements ni capital K ay bounded below by one of the function values in the set and bounded above by another element of the set itself. And that ends the proof. Napakita na natin na yung minimum at saka yung maximum ay nasa loob ng set K na yon. Or merong mga elements ng domain, mga elements ni capital K na makakapagbigay sa atin ng minimum value at maximum value ng function over the set K. And that ends the proof. Okay? Tapos napaka-far-reaching ng applications ng Theorem 3.7. Kaya usually, pag nagsosolve tayo ng optimization problems, gusto natin laging ang domain of definition o ang feasible set natin ay compact. Kasi kapag compact yung ating domain o yung feasible region, ibig sabihin laging may sagot yung optimization problem na nandun sa feasible region na yon. Okay. So the existence ng mga maximum and minimum values are actually most often hinged on the extreme value theorem. Okay? So questions. Grabe, umulan ng malakas dito sa amin for siguro about 10 to 15 minutes. Tapos tumila na siya ngayon, tapos ang lagkit sa pakiramdam. So, yeah. Sarap tuloy mag-shower after mag-klase. No? So, bilisan na natin. Pero sige, 2-minute break muna tayo para makahinga-hinga tayo ng konti. Saka para ma-digest niyo yung mga pinagagawa natin. The next thing will be uniform continuity, right? Pero hindi ko tatapusin itong 3.5. Siguro yung dalawang main points lang. Tapos itutuloy natin on Tuesday. So habang intermission number tayo, meron ba kayong mga gustong i-share? May mga concerns gustong itanong? 155 related or not? Yan, syempre as usual, tahimik na naman kayo. Yan siguro yung isa sa mga nami-miss ko sa face-to-face, ano? Yung ingay ng mga estudyante na minsan kailangan ko pa silang sawayin. Nami-miss ko yung yung mga tipong okay children, yung sisigaw ka ng ganun sa klase kasi super ingay na nila. Tapos pag nilapitan ko, makikita ko yung ginagawa nila yung homework dun sa kabilang klase. Pero na-realize ko, okay, mabait pa pala yung mga estudyante. Kasi nung bumalik ako sa pagiging estudyante nito, kailan ba yan? Siguro mga last year or 2 years ago, pagka talagang hindi ko na naiintindihan yung tinuturo ng teacher namin, wala na, magbubukas na lang ako ng Amazon o ng eBay. Kaya ang gastos umattend ng klase kasi napapa-shopping ng hindi oras, ano. Kasi ang hirap naman na pag in-add to cart mo, hindi mo i-check out. Kasi nangyari sa akin na iisipin ko pa yan ng matagal. Parang hindi ako makapag-focus. Kasi pag-iisipan ko siya kung i-check out ko ba o hindi. So, naapektuhan yung aking well-being. So, sige na nga, kung meron naman akong resources, sige, i-check out ko na. So, magastos pagka hindi ka nakikinig sa klase. So makinig. Ayan, nawala ako ng konti ron, but go back. So let's resume. Let's look at section 3.5, which is about uniform continuity. Now I realized, siguro last semester when I was teaching uniform continuity rin, I realized na yung konsepto pala ng uniform. Sorry, nawala yata uli ako. Yeah, so I was saying na when I was teaching it back then, I realized na mukhang kamukha to ng konsepto ng mga Cauchy sequences. Kasi kapag meron kang ang isang sequence ay Cauchy, kapag habang ikaw ay palayo ng palayo dun sa listahan, nagiging mas dikit-dikit yung mga elements ng sequence o mga terms ng sequence. So, pwedeng nandito si X1, nandito si X2, pag nandun ka na sa dulo ng listahan, dapat mas palapit na ng palapit yung mga terms ng sequence sa isa't isa. Yun yung kailangan natin sa pagiging Cauchy. So, ito ay mas powerful o mas restrictive kesa sa konsepto ng continuity. Sorry, not continuity, convergence ng isang sequence. Kaya sabi natin, nagko-converge ang isang sequence kapag in the long run, yung mga elements ng sequence ay palapit ng palapit dun sa limit. Pero kapag Cauchy yung sequence mo, hindi lang sila palapit ng palapit sa isang number, pero palapit sila ng palapit sa isa't isa. Alright? So ibig sabihin, it doesn't matter kung sino yung limit, basta yung mga elements ng terms ay nagkukumpul-kumpulan habang palapit ka na sa dulo. Palapit ka ng palapit sa dulo. So parang mas magkakabarkada yung mga nasa dulo ng listahan kaysa dun sa mga nandun sa unahan. Alright, so yun yung pagiging Cauchy. And we have learned that at least in the set of real numbers, any Cauchy sequence is convergent and vice versa. Yun yung Cauchy convergence criterion na diniscuss natin way back in unit number 1. Now, medyo kamukha nito yung konsepto ng uniform continuity. Number 1, this is a special type of continuity. Ibig sabihin kapag uniformly continuous ang isang function, automatically siya ay continuous. But the converse is not true. There are continuous functions that are not uniformly continuous. Well, what does it take to be uniformly continuous? Una, ang uniform continuity pala ay defined ay description sa isang set. Okay? Walang uniform continuity at a number. Lagi itong uniform continuity at on a set. So dapat set yung kino-consider mo. Sets yung tinetest mo for uniform continuity. Now, kailan siya nagiging uniform continuous? Dapat uniformly continuous siya kapag kaya mong palapitin, kaya mong paglapit-lapitin yung mga function values by simply requiring yung mga x elements to be closer and closer to each other. Now, this is a little bit different from continuity. Kasi sa continuity, ang goal mo ron ay mapalapit ng mapalapit yung mga function values papunta dun sa function value ng isang number. And you want to do that by making x very, very close to x sub 0. Okay? Pero sa uniform continuity, mas malaki yung requirement. Dapat yung mga f of x's ay palapit ng palapit sa mga f of y's, where x and y are very, very close elements of the domain. Tapos kaya siya tinawag ng uniform continuity kasi remember, sa epsilon delta definition ng continuity, dapat sa kahit na ng epsilon, makapagbigay ka ng delta. And usually, that choice for delta will rely on the number x sub 0 kung saan tinetest nyo yung continuity. So, laging merong mga functions na, yung choice mo ng delta nakadepende rin kay x sub 0 kung sinong number yung tinetest mo for continuity. Pero kung nagkataon na sa kahit na anong element ng domain o nung set, yung choice of delta ay hindi nakadepende dun sa x sub 0. Okay? So, ibig sabihin, kahit saan mo pa chine-check yung continuity, laging isang klaseng delta lamang ay pwede mong gamitin. sa lahat ng elements ng set. Ibig sabihin, merong uniform na delta sa lahat ng elements ng set na yon, then we can conclude that there is a higher level of continuity possessed by the function on that set. And we call that uniform continuity to pay homage to the fact na uniform yung delta na ginagamit natin. Now, some specific examples. Halimbawa yung linear function, the identity function, f of x equals x. Now, if you will do the preliminary analysis, okay, pwede mo ipakita na si f ay continuous sa kahit na anong real number x sub 0. Okay? Pero sa proof na yon, magpe-preliminary analysis ka, given ka ng epsilon, ang makukuha mong delta ay equal kay epsilon. Or makikita mo na, okay, kahit ano pang epsilon ang binigay, ang response na delta na ibibigay ko ay yung epsilon na rin na yon. And notice that this epsilon or that choice for delta ay hindi nakadepende kay x sub 0. So if you want to test kung continuous si f kay say x sub 0 equals 1, pag binigyan ka ng epsilon, yun na rin yung delta. Kapag gusto mong i-test yung continuity ng function at x sub 0 equals 7, si delta na rin, si epsilon na rin, pipiliin mo na value ni delta. So across any x sub 0, all throughout the domain, pwede mo mapakita na continuous yung function by choosing the delta to be equal to the given epsilon. Yun yung ibig sabihin ko na yung delta ay hindi nakadepende kay x sub 0. And because that happens, then we can conclude that this is uniformly continuous all throughout the set of real numbers. Kasi nga sa lahat ng x sub 0, kahit ano pang element ng domain, sufficient, nakakahanap tayo ng delta na mag-work sa kanilang lahat para masatisfy yung epsilon delta definition ng continuity. Okay. In contrast to functions like x squared, magpe-preliminary analysis ka para kay x squared. Continuous to sa lahat ng x sub 0, right? Na sa lahat ng real number kasi polynomial yan. Polynomials are continuous everywhere. Pero ang problema, continuous nga siya pero hindi uniform yung continuity. Kasi kahit na ano pang preliminary analysis yung gawin mo, yung masosolve mo na delta ay laging magdedepende kay x sub 0. Okay? Yung classical preliminary analysis, halimbawa, hindi ko maalala kung ginawa natin to dito sa klase, pero probably in Math 36 you did this. Pag binigyan ka ng epsilon greater than 0, isang posibleng choice for delta is the minimum between 1 and epsilon over 2 times the absolute value of x sub 0 plus 1. And it is apparent that the choice of delta is dependent on x sub 0 kasi dun sa formula ni delta, kasali si x sub 0. So ibig sabihin, kung gusto mong i-test yung continuity at say x sub 0 equals 1, then ang delta na pipiliin mo ay yung minimum between 1 and epsilon over 3. Okay? Pero kapag yung x sub 0 mo na kung saan mo tinitest yung continuity in x squared ay equal kay 5, yung delta mo na would be the smaller between 1 and epsilon over 11. So magkaiba na yung delta na kailangan mong gamitin para sa dalawang magkaibang x sub 0s. So therefore, there is no uniform delta here. And I can guarantee you na kahit ano pang PA yung gamitin mo, kahit magkaroon ka pa ng minimum of 7 and another number, or minimum between 0.0001, yung kalaban niya sa minimum ay laging mag-involve ng x0. And so we can say that x squared is an example of a continuous function that is not uniformly continuous, because the choice for delta depends not only on epsilon, but also on the x sub 0 at which you want to check continuity at. Okay? So yun yung konsepto, pero nauna na yung examples. Formally, ano nga ba yung ibig sabihin ng uniform continuity? Well, basically yun lang, yung sinabi ko kanina. Dapat yung choice for delta for some given epsilon should be independent of x sub 0. In particular, dapat, given an epsilon greater than 0, we should be able to find a delta greater than 0 that depends only possibly in epsilon, such that for all elements of the domain E, right, the the fact that the distance between x and y is bounded above by delta should imply that the function values will have distance bounded above by epsilon. So dapat kapag ka yung x minus y ay less than delta, dapat mag-follow na yung f of x minus f of y ay less than epsilon. Now, nabago siya mula dun sa plane continuity. Kasi sa plane continuity, hindi to x. X sub 0 yan. Tapos ito ay f of x sub 0. Tapos si x sub 0 ay fixed. Alright? Naka-fix siya dun sa x sub 0 kung saan natin gustong evaluate or gusto nating i-test yung continuity. Pero sa uniform continuity, wala tayong x sub 0 na tinitingnan. Kasi gusto ko mag-hold itong delta and epsilon inequalities sa lahat ng x at y na nandun sa set E. Kaya sabi ko rito, ang usapan sa uniform continuity ay sa buong set. Alright? Kasi gusto nating makita na ito ay totoo sa kahit na anong dalawang miyembro ng domain. Walang naka-fix sa kanilang dalawa. Silang dalawa ay arbitrary members of the set E. Okay? Kaya dapat dito talaga yung delta ay hindi nakadepende kay epsilon. Which reminds me, parang meron pa tayong isang nakitang example ng hindi uniformly continuous. Yung paborito natin sa 155 na square root of x sub 0. Okay? Dito sa square root of x sub 0, okay? Sorry, na-distract ako. Meron akong nabasang email. Pero anyway. So, dito sa f of x equals x sub 0, sabi natin para mapakita na to ay continuous over the set E, which is the set of all positive, non-negative real numbers. And kapag kasi x sub 0 ay hindi equal kay 0, ang choice natin for delta ay square root of x sub 0 times epsilon. Okay? Tapos, I can guarantee na kahit ano pang preliminary analysis yung gawin nyo, yung formula na makukuha nyo para kay delta, laging mag-i-involve ng x sub 0. So yung square root function ay hindi uniformly continuous, and yet it is continuous. Okay? So medyo mahirap na mag-prove ng uniform continuity using the definition. Okay? Kaya kailangan natin ng mas operationalized na criterion or characterization for uniform continuity. Okay. Now, yun yung binibigay sa atin ng Theorem 3.8. Excuse me guys for a second. Okay, sorry about that. I'm back. Hindi ko na kinaya yung runny nose, so I need to do some things to get rid of it. Pero yun, where were we? Yeah, I'm introducing Theorem 3.8, which is basically a characterization of uniform continuity. And the nice thing about this characterization theorem is that it goes back to limits of sequences again. What is it? Well, meron ang isang function daw ay uniformly continuous sa isang set E if and only if for any pair of sequences in the domain whose limit or kapag meron kang dalawang sequences dun sa domain, tapos kapag ka nag-construct ka pa ng isang sequence, ang sequence na xn minus yn, tapos nag-converge daw yon kay 0, then dapat magfa-follow na yung sequence of differences between function values ay magko-converge din kay 0. So essentially what happens here is that you take any two sequences, okay, for all to, so kahit anong dalawang sequence na nandun sa domain, such that super magkakalapit or palapit ng palapit yung mga terms nila sa isa't isa. That's the only way that x sub n minus y sub n will have limit equal to 0. Ibig sabihin, palapit sila ng palapit sa isa't isa, magfa-follow daw na yung function value yung difference ng mga function values ay dapat isa ring convergent sequence. And that sequence should also converge to 0. Okay? So this is a good characterization for uniform continuity. But again, a disclaimer first, mahirap pa rin siyang gamitin para mag-prove ng uniform continuity. Kasi kailangan para makapag-conclude ka ng uniform continuity, dapat magawa mo to or ma-check mo to sa lahat ng posibleng pares ng mga sequences na nanggagaling dun sa domain, which is almost impossible to do, or it's impossible to do all the time, right? So, pero maganda tong characterization sa kung alam mo na uniformly continuous ng isang function, then you can deduce some properties by taking advantage of this result. Alam mo kasi pag siya uniformly continuous, totoo tong implication na to. So, pwede kang gumamit ng mga theorems from Unit 2 para ma-prove yung mga bagong theorems about uniformly continuous functions. Okay? Tapos yung converse, siguro mas maganda siyang tingnan as a test for pagiging hindi uniformly continuous. And I think that is theorem 3.9, pero next time na natin yan i-discuss. Right? So what we'll do now is to cap off the meeting. I thought I can dismiss you early today, pero tapusin lang natin yung proof ng theorem 3.8. Medyo maiksi lang naman yan. Okay, now, Theorem 3.8 is biconditional. So, ibig sabihin, if and only if yan, so dalawang parte yung proof natin. Yung forward implication at saka yung kanyang converse. Okay? Kung siya, umpisa natin sa forward. Dun sa forward implication, i-assume natin na siya uniformly continuous. Tapos gusto kong ipakita na pag kumuha ako ng kahit na anong dalawang sequences, na yung sequence of differences ay nagko-converge kay 0, i-imply nun na yung sequence ng difference ng function values ay magko-converge din kay 0. Okay? But the nice thing here is our hands are tied. Kasi isa pa lamang naman yung alam natin about uniformly continuous functions. Yun yung nanggagaling sa definition. Okay? So del CF a uniformly continuous, then definition says for all epsilon greater than 0, we can find a delta greater than 0 such that regardless of elements of the domain x and y, this inequality is true. Okay? All right. So totoo daw yan. Now, since we are proving or we want to show the truthfulness of an implication, conditional proof yung gagamitin ko, mapapasama to sa assumptions natin dun sa forward case. So we will assume that we have two sequences, xn and yn, such that the limit of the sequence of their corresponding the sequence of the difference of corresponding terms in the sequence converges to 0. Okay? Gusto kong ipakita na kung ito ay totoo, magfa-follow itong limit statement na to. Okay? So kumuha tayo ng dalawang sequence, xn and yn, assume natin na yung xn minus yn nagko-converge kay 0. Okay? Dahil yan ay nagko-converge kay 0, sa kahit anong epsilon greater than 0 na piliin ko, laging may starting index na yung xn minus yn minus 0 ay less than epsilon. Since that will be true for any epsilon greater than 0, it must hold for the specific delta na nakuha natin mula dun sa uniform discontinuity. Kasi siya ay greater than 0, yung definition ng limit ng sequence nag-hold siya sa kahit anong positive number. So itong delta na to, siya yung gagamitin ko dun sa definition ng limit doon sa sequence xn minus yn. So ibig sabihin, for the same delta as above, we can find a starting index capital N after which yung absolute value ng xn minus yn minus their limit, but their limit happened to be equal to 0. So kaya nawala na yun ng subtrahend. So natira na lang na xn minus yn ay less than epsilon. Pero yung specific epsilon na ginamit natin ay delta. Okay, so in-apply ko yung definition ng limit ng sequence. So this is so that is true, right? But what is the nice thing about that? We know that xn minus yn are both coming from the domain, all right? And their difference is absolute value less than delta. Pero sabi nung assumption natin, kapag meron kang dalawang numbers na yung distance from each other ay less than delta, yung function values nila ay magkalapit na rin within epsilon units. So this inequality will apply, so that means yung function value nito minus yung function value nito ay magiging less than epsilon. And that's what we get over here. Okay? But what does that mean? That means that for any epsilon greater than 0, there exists a starting index capital N, after which, okay, yung f of xn minus y sub n minus 0 ay less than epsilon. So ibig sabihin yung limit ng f of xn minus f of yn ay dapat equal kay 0. And that's what we wanted to show. Right? So we're done with the forward implication. Now, gawin naman natin yung converse. Ano ba yung sinasabi ng converse? Or ano yung gusto nating ipakita sa converse? Gusto nating ipakita na kung sa kahit anong dalawang sequence, such that the limit of xn minus yn equals 0 implies the limit of f of xn minus f of yn equals 0, then sure tayo na si f ay uniformly continuous. Okay? So that's what we want to show in the converse. So we will assume that this part is true. And then we want to show that f is uniformly continuous, but I will do so by contradiction. So I will suppose, for the sake of contradiction, that f is not continuous. Okay? Kung siya ay hindi continuous, kailangan lang nating i-negate yung definition ng uniformly continuous. That means there exists an epsilon greater than 0, let's call it epsilon sub 0, such that sa kahit na anong delta na piliin natin, including deltas equal to 1 over n. Okay? So we have the delta inequality is true, but the epsilon inequality is false. All right? So ito yung negation ng uniform continuity. Now, dahil meron tayo nito, ibig sabihin nito na ito, ang ibibigay niya sa atin ay yung limit ni xn minus yn ay equal kay 0. Kasi kung yung xn minus yn has absolute value that is always bounded above by 1 over n for any n, all right, then we don't have any choice but to conclude that xn minus yn must approach 0. Kasi pag hindi ito nag-approach ng 0, ibig sabihin merong mga terms na malaki yung subscript na hindi sila magiging less than 1 over that subscript. Okay, so we will be forced to conclude this. However, part ng ating assumption na kapag ka ito ay totoo, ito dapat ay totoo rin. So that means this guy will imply that the limit of f of xn minus f of yn is equal to 0, but that will contradict our assumption that f is not uniformly continuous. Okay, sabi natin, hindi siya uniformly continuous, so dapat makakakita tayo ng isang epsilon sub 0 kung saan yung f of xn minus f of yn ay greater than or equal kay epsilon sub 0. So that means f of xn minus f of yn cannot converge to 0. Kasi nga merong isang epsilon na laging mas malaki yung distance kaysa kay between f of xn and f of yn. So imposible daw to na mag-converge kay 0. And yet here we are, by virtue of our assumption na sinasabi natin na dapat magko-converge yung f of xn minus f of yn kay 0. Okay? So that's the contradiction. So that means it's impossible that f is not uniformly continuous. So we need to conclude accordingly that the converse is also true, thus ending the proof. Medyo i-edit ko yung proof na nakasulat yung sa converse kasi merong mga detalye na hindi siya kasama. Yun yung kwento ko sa inyo ngayon. So I'll try to revise the proof in the next iteration of the lecture notes, which I hope to be able to give you Monday next week. All right? Now that's the end. Next time we'll talk about sequential criterion for non-uniform continuity, and probably I'll share a couple of thoughts bakit importante yung uniform continuity. Okay? So guys, do you have questions? So I've turned on, so thank you guys for joining me today. Again, watch out for the homework that I will release tomorrow. The deadline is on Tuesday next week. And then tingnan natin yung then problem set will also be given pero late next week na. Oh, that's nice to know, Charles. Thank you for letting me know. All right. So sana laging ganyan o nakakasunod for lecture. Tapos kung hindi man, don't feel bad. You can ask questions. I don't think there are stupid questions. All right. So I'll try my best to answer questions kung meron man. So huwag kayong mag-hesitate na magtanong. All right. So if there are no other concerns or questions, then thank you guys for joining and magkita-kita tayo on Tuesday. Pero enjoy nyo muna yung weekend. So, but keep the process. All right? Bye, guys.